This is the test on impulse and momentum conservation laws. So this test is really important because that you will have a clear understanding of how to deal with vectors and forces and momentum, and what is the impulsive force, what is the impulse. You will have a precise understanding. So even though you get answers correctly, I suggest you watch the whole thing, because there are some key points that you have to identify when you are doing the question. For an example, how to apply the directions correctly. Sometimes you might get the answer correct, but you might not understand how to apply the directions precisely. So even though you for this question get the answer correctly, for another complicated question you might get the answer wrong if you are not following that correct method. So I suggest you watch the whole thing, even though you get the question, even though you answer correctly for that question, right? Okay, keep that in mind, and we'll be move on to the first question, right? First one, physical quantity with the same dimensions as impulse is, right? So they're asking about first about dimensions. So that is a, so you know this equation, right? So this is based on F equals ma. If you cross multiply, you get F times T equals mv minus mu. Then I is equal ft equals mv minus mu. So this is the equation impulse, and this momentum, dimensions of momentum change also, you get a momentum, right? So dimensions of momentum and the impulse, they are the same. So rate of change of linear momentum, it is not the answer. Rate of change of linear momentum means force. Force and impulse, there are two different concepts. So rate of change of momentum means force. Momentum change means impulse. Change of momentum is impulse. So it should be the second one, right? Linear momentum. Second one, speed gained by an object when an impulse 10 Newton seconds is acted on an object with mass 2 kilogram. So you can treat the impulse similar to force, okay? Impulse is 10 Newton seconds. 2 kilogram. So let's say initially the velocity of the object as 0, because they're asking about a gain of velocity. Right, let's say it gains a velocity v. So you just apply this equation, I equals change of momentum. So let's consider the directions. For this example, directions are not that important, but let's see how to apply directions correctly. So the momentum is to this side, so plus 10, right? Mass is 2, velocity is, this is final velocity, this is initial, this is final. Final velocity v, initial velocity, it is at rest. So 2v is equal to 10. So v should be equal to 5 meters per second, right? So that is how. So it is true that finally the velocity should be to this direction, obviously, right? So it agrees with the equation. So you got a positive value. It is obvious, but for in other cases also, if you apply directions correctly, you need to get the positive answer. If you get a negative answer, meaning of that is direction is to the opposite direction. I reminded you that in when we are doing the test on Newton laws as well, right? So, right. So in most cases, you will get the accurate answer, accurate. But if you get a complicated question, then that's directions are going to be important, right? That's why for the simple ones as well, you have to apply, you have to think about the directions. So we'll get used to that, right? Okay. Third one, an object with mass 2 kilogram, an object with mass 2 kilogram is moving to right side means this side, at 5 meters per second. Is submitted to 3 Newton left. 3 Newton is to the other side. And the time for that is for 3 seconds. So 3 Newton is applied for 3 seconds. Velocity gained by the object. Let's say final velocity is v, right? So the velocity changes because of this force. Let's say the final velocity is v. So if we get a negative answer, this v should be to the opposite direction. But let's see what happens. So I'm using, since the force and time is given, I'm using Ft in order to find the impulse. Ft is equal to mv minus mu. I'm applying the equation to this side. Since I'm applying the equation to this side, force is to the opposite side, so you get a minus 3 for the force. And the time is 3, right? Mass is 2, final velocity I took it as v, and to this direction, so positive. Minus mass 2 times u. Initial velocity also this direction, so positive value, 5. So 10 minus 3, sorry, 10 minus 9, it is 1 equals 2v. So v should be equal to 1 over 2, that is 0.5 meters per second. That is 0.5 meters per second. And we got a positive value, see that? Meaning the direction we marked here is correct. So it should be to the right direction. It is still moving to the right direction, right? So the answer should be, isn't the answer given there? It should be to 0.5 meters per second to right direction, right? So the answer should be first one, okay? Answer should be first one, right? Fourth question, an object with mass 2 kilogram which is at rest, 2 kilogram at rest, which is acted upon by a force capital F. Variation of force is given below. So if the force is not constant, they have to give the variation as in a graph. They give the variation of force in a graph. Then the area of that graph, net area of that graph, is equal to the impulse or the change of momentum. So here you have 4 and 4, 6, and this value minus 2. So this one you can see 4 times 4, it is 16 Newton seconds, and this area minus 2, and this is 2, 2 times 2, that is 4, right? But this is a negative area, right? So impulse is equal to always mv minus mu. Here the impulse, you cannot apply Fs. Just you cannot apply Fs if the force varies, right? So you have to, not Fs, I mean Ft. So you have to consider the area of the Ft graph. So the net area is 16 minus 4. This is equal to let's say the mass is 2 kilogram, velocity is v, minus, initially it is at rest. So this is 12 equals 2v. So v is equal to 6 meters per second, right? So velocity is equal to 6 meters per second. So for the previous questions, you just get the impulse by multiplying f by t. But that is only when the force is constant. But here the force is variable. It is constant only for one period, right? So in that case, they give you the graph. Then you have to find the impulse using the graph. The area of the graph is the impulse, right? Right, fifth question. An object with mass 5 kilogram at rest 5 kilogram at rest is acted by driving force F and resistive force R, right? So this is a very important question. Variation of the forces are given in the graphs. So this is a variation of force time. I mean driving force, variation of driving force time, and 10 here 20. So for these questions, you cannot apply uh, motion equations. You cannot apply because the force is varying, right? So if the force is varying, acceleration of the object also varies. So it is not possible to apply motion equations for these cases. So you have to apply, the only way is to think about the applications of impulse here. Right, so this is then resistive force. It is like this, here 10, here you have 8 and 5 and then 10. So these are the variations. So the both have the same time periods up to 10 seconds, right? Up to 10 seconds. Right. So what they ask is when t is equal to 10, what is the velocity? Right. So this is ft equals mv minus mu, right? Listen carefully, you have to understand this. This F is actually the unbalanced force, not this F, right? This is just driving force. F is unbalanced force. So instead of this F, I can apply F minus R. So it should be F minus R times T. Got it? This is not driving force, right? This F means you get this from the F equals ma. So this force is unbalanced force. So it is F minus R times T. Then you get mv minus mu. Since initial velocity is 0, I am just removing this part, right? It is 0. So it is mv. So then you get ft minus rt equals mv. Even though you write it like this, there's a simple, there's a small error here. Actually, you have to integrate this, right? You have to integrate this f by t. But integration is not in the syllabus, right? So we'll try to understand this in some way. So ft, this force is a varying force. You cannot just multiply f by t. So there's another method. So that method is just get the area of the graph, area of the ft graph. So area of the ft graph is what? It is a triangle. So it is 20 times 10 divided by 2 minus. Then to find RT means actually this R is varying, right? The R does not have a one value. It is varying according to this. So to find RT, you need to integrate. Another way is to get the area of the graph. Integration is not in the syllabus, right? So that's why you need to find the area of the graph. So let's find the area of the graph. So there's a triangle and a square. So let's get a square first. This is 5 and this is 8. So just 5 times 8 plus, for the triangle it is 5 times 10 divided by 2. 5 times 10 divided by 2. So this is equal to, mass is 5 kilogram and we have the V. So all you have to do is just simplify this and find V. Let's see, so it is 10 times 100 minus, this is 40 plus 25. So it is 65. 5 is equal to 65, so you get 35. 35 divided by 5 is 7 meters per second. So that's the final velocity, right? So for a question like this, it is not possible to apply. It is not possible to apply that motion equations, because at none of these times there's a constant acceleration, right? Motion equations can only be applied to acceleration, constant accelerations, right? There's no constant acceleration. It is here. It is increasing here. I mean, according to this one, it is. It is complicated, right? So the only way is you have to get the area of the graph. So this is the correct procedure to approach this question. So this is an important question, right? Right. Sixth question. It is actually an exam question, but let's get the answer in the correct method, following the correct theories, right? Correct theories, right? I have seen that many explain this using other methods, but once you get this method, it is the most accurate one, right? Because it is exactly following the theories, right? The image shows the variation of force applied by Earth on a person as it jumps up. Weight of the person is 650 Newton. So let's say this is the person. So if he is trying to jump, right? If he is trying to jump up, you know that by earth, by flow, it causes a force on the person, right? The person is applying a force on the ground as earth applies a reaction force on the person. So that reaction force is what causes him to jump, right? To leave the flow. So that is, I'll mark that one as R. Actually here it is mentioned as F, right? So the variation of F is given. This force varies. Then there's the weight of the person, that is 650 Newton. It is a constant force, but this F changes, right? Right. So the graph is given like this. Here you have 0.3. Here you have 0.4. And the value here is 1430. Here the value is 650. Right? Right. So we'll just apply this equation. Ft equals mv minus mu. Even though I have mentioned this as F, this F and this F are not the same, right? This F is unbalanced force. This is normal reaction force. So unbalanced force is what? F minus 650, right? Usually, like in many questions, you only have to apply one force. But when you get a question like this, there are two forces acting here. So for F, you have to put the unbalanced force, which is F minus 650. T equals mv minus, initially the person is at rest. Right. Then you get Ft minus 650T equals mv. Okay. So what is this Ft? This F varies, right? So I have to integrate. Another method, you have to get the area of the graph. Area of this whole thing gives us Ft, value of Ft. Then you have to subtract 650 times T. So what is 650 times T? Isn't that this area? This is 650 and T is the given time, right? 650 times T. So what does it say? From the whole area, if you subtract this area, you get the impulse. Impulse means this Ft. Here F and here F, two different things, right? Even though I use the same symbol, because in the question it says like that. This F and this F different, right? This F means unbalanced force. This F is actually, it should be R actually. Doesn't matter. In the exam, it is given as F, capital F. So use it, doesn't matter. So impulse should be this area. Okay, so this is the correct explanation why you have to consider this area for this question. Okay. Okay, so let's find the area here. So you have a trapezium. So this is 0.1. This is 0.4. This is 0.4. 0.1 plus 0.4 divided by 2 times. This length is 140. I mean 1430 minus 650. So this is equal to mass of the person is 65. So if you divide by 10, you can get 65 kilogram. And you have V. So from V, you can get the velocity as he leaves the flow. The moment he leaves the flow at this velocity. Whatever the velocity you get here. Right. So you have, so this is 0.5. 0.5 divided by 2 times. So what do you get here? 13, 650. 0, 13, 8. 13 minus 6, that is 7, right? 780. Okay, I'll just divide this. You get 390. 390 means you have 3 13s. And you have 0 here. 30. Both sides divide by 13. So 5. Okay. Then this 5 and this cancels off 0.1. 0.1 times 30 is 3. So this is the velocity the person leaves the flow, right? So the initial velocity of the person leaves the flow is, that is initial velocity, that is 3 meters per second, right? If they want, they could extend this question further. They could ask how much of a height he reaches, right? So for those you can just apply. After that, you can apply motion equations to get the values for those. But here you have to consider the impulse, right? Right, seventh question. So the remaining questions are from momentum conservation, okay? A bullet with mass 0.1 kilogram moving at 450 meters per second hits and is stuck. So this is the first case. Second case is the bullet is inside. So the total mass is 0.5 kilogram and it is stuck. So both have the same velocity. Velocity of the bullet and the mass is. So that is what they are asking is common velocity, right? So this is a perfectly inelastic collision. Because you know that when the objects have the same velocity after colliding, those types of collisions we call them perfectly inelastic collisions. So they have the maximum kinetic energy loss. Okay, let's here you don't have to worry about kinetic energies. You just have to apply linear motion. I mean linear momentum conservation. Right here, speed 450 times mass. This is not moving, so momentum 0. This is the momentum before collision. Then that is equal to the momentum after collision, right? So the collision does not cause a change of momentum in the system. So that's the theory, right? So here the mass is actually 0.5 times velocity. So here you get 45, 0.5 is 0.5 means half. So cross multiply, you get 90 meters per second. So that's the velocity that this whole thing would move after the bullet hits the block, right? So that is 90 meters per second. Sorry, here it is 1.5, right? When it hits here, the mass is, when you add that, it is 1.5, not 0.5. Okay, it is 1.5, right? Okay. So 1.5 means 3 over 2. So you get 15 times, that is 30 meters per second. Yeah. So it is 30 meters per second, right? After colliding, it moves at 30 meters per second. Right. Eighth question. An object with mass 3 kilogram moving at velocity v explodes into two parts with 1 kilogram and 2 kilogram. Large moves to the same direction at v over 2. So they ask velocity of the small part. So you know, at an explosion as well, the momentum of the system does not change, right? So for at an explosion, what you have is equal and opposite forces acting at the moment of explosion. So these forces does not change the momentum of the system. So you can say momentum before equals momentum after the explosion. So 3 kilogram moves at v. 3 kilogram moves at v. Then explodes. After the explosion, large part moves to the same direction. Let's say this is 2 kilogram. This moves to the same direction at v over 2. Then what they ask is velocity of the small part, right? So this is the before collision situation. This is after collision situation. So for the system, momentum is conserved, doesn't change, right? Cannot change without an external force, right? So before momentum is 3 times v equals after momentum 2 times v over 2 plus this one 1 times v. Now we don't know this velocity, right? So I take it as u. You don't know this velocity. It is not v. That is what you are finding. So here you get v. 3v minus v is 2v. So u is equal to actually 2v, right? 2v. So the answer is fourth one. That's a simple question. Right. Ninth question. A clay ball with mass 0.05 moving at 10 meters per second, 0.05 kilogram, 10 meters per second is incident with another clay ball with 0.06 kilogram at 12 meters per second to the opposite direction, right? After them being incident, they stuck together. Velocity of the compound object is. So this one also is perfectly inelastic because they stuck together after the collision, right? Maximum kinetic energy loss. So because this has more momentum, I'll just so they stuck together like this. Then let's say the velocity of the compound is just v, right? And I just mark that to this direction because after collision, they should move to the other direction, right? Even though you marked it to the other direction, it doesn't matter. You would get a negative answer for that one. You can correct that. You can say that it is to the opposite direction, right? Here, I just apply the equation to this side because I know this momentum is larger, right? It doesn't matter which direction you apply that, okay? If you correctly substitute terms with the directions, at the end you get the correct answer there. So if you get a negative value, all you have to do is to say that it is to the opposite direction, right? So momentum here, before collision, it is moving to this direction. So I am putting minus 10 times 0.05. This is moving to this direction, right? So it is a positive. So that is 12 times 0.06 equals total mass. Here they move together, so you can consider the total mass. 0.05, 0.06, so it should be 0.11 kilogram times V. Now just simplify that in order to find velocity. So this is a MCQ, so the simplification is going to be simpler, right? It's not going to be complicated. Right. So let's say here, so you get, when you multiply by 10, it becomes 0.5 minus plus, here you have 0.72, 12 times 6, 72, right? 0.11 V. So you get 72.72 minus 0.50. So 2 to 0.22 equals 0.11 V, meaning 1, 1, 2. So V is equal to 2 meters per second. So the direction we took is correct, right? So if you mark this direction to the opposite, you get a negative value. But you can say it is to the opposite direction. Doesn't matter. Answer is third one there. 10th question. So that is a sentence question. So when you are dealing with sentence questions, you have to be careful, right? Whether the sentences follow the exact theory, or else you have to get the most appropriate answer. Sometimes that sentence won't make the perfect, won't describe the theory perfectly. But compared to the other question, other sentences, if it says something right, you have to get the most appropriate answer there, right? Okay. Let's see. So they're asking correct ones. They're asking about the correct question, correct sentences. So let's say impulse on B by A is equal to impulse of A by B in magnitude. So they say collides, just two objects collide, A and B. So when they collide, what happens? It causes an impulse here and an impulse here. So this impulse is by B on A. This impulse is created by A on B, right? If they say impulses are equal, they are not equal, right? Because their directions are opposite. But the question they say about magnitude. Magnitudes are the same, but they are not equal, right? But let's say you get other sentences that are like completely wrong, right? So this sentence could be correct in that case, right? That's why they're asking about the most appropriate answer, right? Even though they haven't mentioned magnitude, the meaning of that could be they are maybe asking only about magnitude in the question, right? So you have to choose the most appropriate. But here you don't have to worry. They exactly say that it is in magnitude. They are not the same vector because they are opposite direction, right? But in magnitude, they are equal. That's true. Then, if only the collision is perfectly elastic, change of momentum of A is equal to change of momentum of B, right? So in this sentence, there are two errors, right? They say, so the A is correct, right? A is correct. They say if only the collision is perfectly elastic, change of momentum. You can think that change of momentum of a one object is equal to I, right? Impulse and change of momentum is the same. So they are equal in magnitude. So that is true for any type of collision. But if they say if only Perfectly elastic. Not true, right? It is not for if only. If they just say for a perfectly elastic, then it is true. So that is the error there. So the sentence B is not correct, right? Uh, the second error is they are saying equal to change of momentum. It is not equal actually. If they say equal in magnitude, then it is correct. So actually there are two errors in that sentence. Actually, so it is wrong. B is wrong. B is wrong, right? Then C. Collision is elastic only if the kinetic energy is not lost due to collision. So that's the definition of elastic collisions, right? Elastic collisions, sometimes they say perfectly elastic, or even though you say elastic, they are the same, right? Perfectly elastic and elastic, they are the same. They can say just elastic. If there's even a small amount of kinetic energy loss, it is an inelastic collision. If the kinetic energy loss is maximum, it is a perfectly inelastic collision. Perfectly inelastic collision. Collision is elastic only if the kinetic energy is not lost. That is true. If it is not, obviously, it is a elastic collision. Right? There are no collisions that does not lose kinetic energy and become inelastic. So obviously it is only if the kinetic energy is not lost. So that is true. C is correct. Right? Okay. So those sentence questions you have to think really logically there, right? Unlike in for other questions as well, but for the sentence questions you have to spend some time understanding precisely what they are saying in the sentence. Right. 11th one. A train carriage with length 11 meters. So this is also important question to understand these external forces, action, reaction forces, those stuff, right? So the length of this given as 11 meters, and the mass of this, the train carriage, that is 1,000 kilogram, meaning it is 1 ton, is on smooth rail tracks, meaning there's no friction acting on this one. So there's no any force horizontally acting on this system, right? Then there's a man weighing 100 kilogram at one of the end. The mass of the man is 100 kilogram. Then the man moves from here to here. So that's what they say. So this length is, if it is 11 meters, this length should be 5.5 meters. Half of that. This whole thing. Half of that distance. It should be 5.5 meters. Then here I'll just find the center of position of the center of gravity. So we have two masses, 1,000 kilogram and 100 kilogram. So that those two masses is at here. I mean, center of gravity should be closer to 1,000 kilogram, right? So you know that the ratio between the masses is, this is 1,000 and 100 means 10 to 1. This is mass ratio, right? So the length ratio, this length, this should be 1 to 10, right? It is the inverse of that mass ratio. Higher the mass, lesser this area. Right. So you can find this distance. Let's say that is O1, and let's say this is G1. So O1 G1 equals what? Total distance is 5.5 meters times total sum of ratios is 1 plus 10, right? You found the ratio, so it should be, the length should be divided into this ratio. So it is 1 and 10. And for this part, it is 1. It is not 10, it is 1. So 5.5, 1 over 11, 0, 0.5. So it should be 0.5 meters. So that is O1 G1. So I just found this O1 G1 length. So this is where the center of gravity of this system, right? So if the man moves to this side, what happens? This similar system, you can say that the new center of gravity should be to this, right? And this distance should be 0.5 meters. It is obvious, right? If the man moves from here to here, center of gravity should be here. It just when the man moves to this direction, center of gravity also moves to this. And as he at this end, center of gravity is at a 0.5 meter distance from the O1 actually, right? So you can clearly see as the man moves from here to here, center of gravity moves from here to here. So how much is the distance? 0.5 plus 0.5. So G1, G2 distance is 0.5 plus 0.5 means 1 meter. So it is a 1 meter. G1, G2 is a 1 meter, right? So what does it mean? Center of gravity of the system has changed from here to here. So you know that center of gravity represents the whole system, right? So if the center of gravity moves from here to here, meaning of that is as if the whole system moves from here to here, but without any external force. Without an external force, horizontal external force, there cannot have a horizontal motion. I mean, right? There cannot have a horizontal acceleration. But it has happened here, right? But it cannot happen. So in order for this to stop, what happens is the carriage moves to the opposite direction by a 1 meter, keeping G1 at the same place, relative to Earth. I'm applying everything relative to Earth, right? Not relative to the carriage. So relative to Earth, the train carriage has to move 1 meter to the opposite side when it's moving to this side, because it is on smooth tracks, right? The train carriage moves to the opposite direction by a 1 meter to prevent this center of gravity from moving relative to the Earth, right? So it is a 1 meter. That is the answer. Fourth one. Right. 12th question. A sphere with mass 10 kilogram moves to right direction at 5 meters per second, collides with an identical sphere, meaning 10 kilogram, moving to left side at 3 meters per second. If collision is elastic, speeds of spheres after collision. Let's say these spheres, this gains after collision, right? After collision, this gets v1 and this gets v2, these velocities, after collision. And they say it is a perfectly elastic collision as well. Okay? So you can just find values of v1 and v2. But the calculation to do that is somewhat complicated, right? I'll just show you why that is complicated. Okay, just let's apply momentum conservation. So it is here initial momentum, that is 10 times 5 plus, this is minus 10 times 3 equals here 10 times v1 plus 10 times v2, right? Then just divide the whole thing by 10. 5 minus 3, that is 2, equals v1 plus v2. So this is one equation, right? v1 plus v2 is equal to 2. Since the collision is perfectly elastic or elastic, we can say kinetic energy before collision is equal kinetic energy after collision. So let's say here kinetic energy before 10 5 squared plus half 10 3 squared equals half 10 v1 squared plus half 10 v2 squared, right? Then I'll just simplify this, so you get half 10, you can get rid of that, right? So that is 5. So this is 25 plus 9. It is, sorry, 25 plus 9. What do you get? 34. 25 plus 9 is 34. 34 is equal to v1 squared, v2 squared, right? So when you get two simultaneous equations like this, you can substitute v1 here. You have to simplify these two, and then you get a quadratic equation, right? Then you get a quadratic equation. You know that for an MCQs, you don't have enough time to do those things, right? For an MCQs, probably there will be another method to approach the question, right? Actually, the method is like this. If the collision is perfectly elastic and the masses are equal, all you have to do is, you have to remember this, right? All you have to do this, after the collision, the velocity changes. I mean, velocity interchanges. So what happens here is, when they collide, velocity of this becomes with the direction, right? With the direction, the velocity of this becomes 3 meters per second. This, right? After collision, the velocity of this becomes 3 meters per second to this direction. And for this, it becomes 5 meters per second to the other direction. See that? The velocity just changed. So in the recent years, they have checked this. You don't have to keep doing this. This is a MCQ, right? So you have to know that. So what are the requirements? Perfectly elastic. And another one is the masses should be same, or the identical objects, right? But I'll just, if you get this in like a essay question, they still, essay questions, you have to do that calculation. But probably you won't get a question like this, because solving this is not physics, right? It is maths. Okay, I'll just show you how to simplify that. So v1 is squared plus, instead of v2, you can apply what? v2 is equal to what? 2 minus v1 squared. So you get 4 minus 4v1 plus v1 squared equals 34. So you get 2v1 squared minus 4v1 plus 4 equals 34. So becomes 30 equals 2v1 squared minus 4v1. Divide by 2. So here you get v1 squared minus 2v1 minus 15 equals 0. Right? So you have a quadratic equation. You have to factor the quadratic equation. So you get v1 squared minus 2v1 minus 15 equals 0. So 15 means 5 times 3. So you get v1 squared minus 5v1 plus 3v1 minus 15 equals 0. So get v1 out, plus 3, v1 out, minus 5 equals 0. So v1 minus 5, v1 plus 3 equals 0. So you can say v1 equals 5 and v1 equals minus 3. So you have two answers for v1. v1 means this one, right? It is either 5 or either minus 3. Still, let's say we cannot say that, cannot get an answer for this. So thinking that, we just simplify this. apply each of these answers to this first equation. So if you say V1 equals 5, so you get V1 equals 5 plus V2. So V2 is equal to minus 3. Here, if you apply V1 as minus 3, V2 is equal to 5. So which set of answers correct? Is it this one or this one? Right? So V2 is minus 3. V2 means the velocity after this colliding at 3 meters per second. Right? So V1 is 5, here V1 is minus 3. So when it collides, it cannot bounces back at the same velocity, right? It cannot bounces back at the same velocity. Therefore, the answer should be this one. So V1 bounces back at a less velocity, minus 3, right? Because they obviously change momentums. So if that bounces back at the same velocity, there's no change of momentum, right? So the answer should be this one. So you cannot do this for an MCQs, right? It is not enough time to do this. So you have to remember that if equal masses collides at an elastic collision, they change their velocities simply. Simply they interchange their velocities. So that's what happens, right? You have to remember that. You are not going to do this. You don't have enough time to do that, right? In an MCQ. Rather than doing this, it's better to move on to another MCQ, right? 13th. So this also is somewhat different but really important to understand, right? There's a key concept here, right? A man weighing simple M in a trolley weighing capital M and moving at V on smooth tracks. Smooth horizontal tracks. Right. So there's a trolley, then there's the man. Both the trolley and the man moves to V. The mass of trolley is capital M, man it is simple M. Both are moving at constant velocity V. He starts moving at U to the same direction of trolley. Then the speed of trolley is, right? So what happens is, then inside the trolley means relative to the trolley, man starts to move to this direction. I'll show that in a second image. So to the same direction. But what happens due to his motion, the velocity of the trolley changes. Let's say V dash, right? But as a result of when the man moves, he has to put steps, right? But he has to apply a force on the trolley. But the thing is, the trolley also applies a force on the man. So if you take this as a one system, those forces becomes internal forces. So those internal forces cannot change the momentum of the system. So you can say the momentum here, total momentum of the system here is equal to total momentum of the system here. So what is the total momentum here? Capital M plus simple M times V. Capital M plus, that is a total mass, times velocity. So that is equal to, for the trolley I'll just say MV dash. That is for the trolley. Then there's the man, right? Simple M. The important one is finding the velocity of man. Here, the man is moving inside the trolley at U, meaning he is moving relative to the trolley, not relative to Earth, right? So for the previous questions, we didn't get a problem like that, right? So for this one, the man is moving inside the trolley, meaning relative to the trolley. not relative to the earth. So the other thing is, when you are applying this equation, all the terms should be equal to earth. So all the time it should be equal to the earth, right? Remember that. It should be relative to the earth. So you have to find the relative velocity of man, right? The relative velocity of man is v dash plus u. Okay, I'll show that. Let's say man is simple capital M and the trolley is capital T. So what do we need to find? Relative velocity of man, velocity of man relative to earth. Put a T here. So you get Vmt plus Vte. So relative to the trolley, velocity of man, u, right? That is relative to the trolley. Plus relative to the earth, velocity of trolley is v dash. So you can get Vme. So they are to the same direction. You can just add those two to get the velocity of man relative to earth. That's what I got, right? So even without solving, if you are like used to relative velocity, you have solved enough problems, it is obvious. You don't have to do this. You can just take it as v dash plus u, right? But that takes practice. So here what you have to find is v dash, which is the velocity of the trolley after man starts moving. Right, so I have to subject this v dash. So I'll keep that here. And you get mu from this term, right? I'll put it to the other side, minus mu. Then you get, take v dash out, you get capital M plus simple m, v dash. Then just divide by this one. Minus mu divided by m plus simple m. So that is the trolley. That is the velocity of the trolley when after the man starts moving, right? So I think first answer, right? First one. Yeah, it should be the first one. Okay. So the key point here is that you always have to apply, when you apply in velocities, when you are substituting velocities, those values should be relative to a one thing, right? Here it is relative to earth. Everything should be relative to earth. You cannot have this term relative to earth and other thing relative to trolley. Everything should be relative to the earth, right? 14th question. So that also is a sentence question and an exam question as well. I included here because it is really important. They always have checked this in the recent papers, right? So they are going to do the same for the remaining ones as well. Okay. A particle with mass m1 moves at positive direction of x at v and elastically collides with a mass m2, and the m2 is at rest. Collides here and m2 is at rest, right? After collision, and another thing is this is an elastic collision, right? Or the perfect elastic collision. Okay. After collision, incorrect sentences. So the thing is, for each sentence, you cannot be applying momentum conservation and kinetic energy equals kinetic energy equation. No loss of kinetic energy thing, right? It is complicated as you see in the previous question. So you have to know what happens. You need to have a slight idea what happens when they collide in an elastic collision. So for an elastic collision, for a perfectly inelastic collision, you know what happens, right? They get attached and move together. So that is for a perfectly inelastic collision. But for a elastic collision, if the kinetic energy loss is zero, you should know what happens there. You need to have that idea, right? Okay. So for the first case, they say M1 is smaller and M2 is larger, right? m1 m2 moves to minus x. So after the collision, they say m2 moves to this, m1 moves to this direction. Is that they say? Now m1 moves to minus x. Sorry, m1 moves to this direction, m2 moves to this direction after collision, right? So if it is elastic, you need to remember that. If m1 is small, just think like this. You need to think the extreme case. Let's say they say just larger. So this is a very large thing, right? M2. And this is a very small thing. So M2 is at rest. So what happens? This one collides at M2. Obviously, M2 has to bounce us off, right? Because this is a very large object. Just think like that, right? If you think about the extreme case, usually you can get a understanding what happens, right? So let's say M2 is very large. So M1 collides here and bounces off. So it moves. So it is true, right? So M2 could get a uh, velocity to this side. So that is what happens there. Okay. Then they say if M1 is larger. So this is correct. If M1 is larger than M2, this is very large than M2. Consider that a very large object collides with this small object. So what could happen? Could M1 bounces off? Cannot, right? Because it is very large. And the velocity also is large. Both is M2 obviously goes to this side. M1 also goes to this side. The M2 is not enough to bounce this off. So both would start to, after collision, both would move to the plus x direction. Get it? So usually that's what happens, right? If this is large, then they both move to the same direction after collision. Practically you can think about that. But this is only for elastic collisions, right? Elastic collisions, then you just have to think about extreme case. Third one, M1 and M2 both moves plus direction attached together. So whenever two objects attach after collision and move together, what happens? That is called a perfectly inelastic collision, not elastic collision, right? So the answer, incorrect answer one should be that one, third one. So that is the answer. Then you don't have to even think about other stuff. If you think about the fifth one, just for the explanation, if m1 and m2 velocity of mass is v. So other thing is, if masses are the same, what happens? I mentioned this earlier. If masses are the same, they interchange their velocities. So this is at rest. So when it collides, what happens? Mass, velocity of this one comes to this. So velocity of this is stops, and this gains this velocity. So it gains v. So they have interchanged their velocities, given that their masses also same for the elastic collision. We already have the answer, the incorrect one. That is third one. So the third one is the answer there. Right. 15th. Two masses are placed on a smooth plane as shown by the image. A moves at 2 meters per second. The mass is 2 kilogram. There's a spring here. And then you have B, weightless spring, massless springs. And this has a 6 kilogram. What is the maximum energy that the springs can attain? Meaning can store, right? This one is at rest, right? They haven't mentioned a speed, so it is at rest, right? So this question also is important. I think this question is from 2020. So what they're asking is, let's think about kinetic energy. So this is before collision, right? before collision kinetic energy. So that is, this is at rest and only this is moving. So 2 kilogram at 2 meters per second. So that is half 2 times 2 squared. So it is 4 joule. 4 joule is before collision, right? Before collision. Right. So they are asking the maximum energy that can store in the springs. So that happens when the springs contracts to a maximum value, right? Contracts to a maximum value. So what happens here? Let's say these two collides, and the springs are like together, right? Together. Still this has 2 meters per second and this is at rest. So with time, so they start changing their momentums. So with time what happens? So this is pressing against A, speed of this decreases, right? Speed of this decreases 2 meters per second. So let's say the speed decreases and comes to V. And speed of B increasing. Speed of A decreases and speed of B increases, right? They are moving to this side, and this for this one, initially it was at rest. The speed of this one is increasing, this one is decreasing, right? Then comes to a certain value. I'll show you that in a graph, right? With time, so let's say initially B has 0 and A has 2 meters per second. And once they touch, after they touch the springs, speed of A decreases because after they touch, there's a force to this side, right? On here, and on B, the force to this side. So speed of A decreases like this, and speed of B increases. Okay. So while this is happening, so these forces also grew up, right? Grew up, and then there's a maximum contraction, meaning there's a maximum force inside these strings. So this pushing stops once their velocities becomes a one value, right? Comes to a one value, their velocities becomes, if they have the same velocity now, they stops their pushing, right? I mean compression of springs stops. Now they are moving to the same direction at the same velocity. Understand? So at that point, they have a common velocity. At that moment, they have a common velocity, and the compression of the springs is maximum. So if you can find the compression at this point, you can find the maximum energy stored in the springs, right? So first, let's find this one. I'll apply momentum conservation for this case and for this case. So for this case, momentum is before collision, that is 2 times 2. This is at rest. Here, in this moment, they are both moving to the same direction at same velocity when it has a maximum compression. So let's say the total mass is 2 plus 6, 8 times V. So we have 4 equals 8V. So V is 4 divided by 8, that is half 0.05 meters per second. Right? Right. So in this case, let's find the total kinetic energy. So this is after collision. After collision kinetic energy. So it is half. Total mass is 2 plus 6, 8. And the velocity is half. Half, then it gets squared. 104, that is, and 2, 8. Then you get 1 joule. So this is the before kinetic energy, this is after kinetic energy. So you can see there's a difference, right? Difference of those kinetic energies. So the difference of kinetic energies must be stored in the spring as elastic potential energy. So the maximum elastic potential energy should be what? 4 minus 1. That is, should be 3 joules, right? Should be 3 joules.